We're going to move into ice, as it looks like. And so Tim Schulze is going to be our first afternoon speaker. He's going to talk about the rapid advance and slow retreat of the mushy zone.
Yeah.
Thank you very much.
Sure. Yeah, mushy zone. So it could be ice, could be rocks, could be chocolate. So the title refers to some work I did with a former student, Nick Uecki, a few years ago. I'll get to that towards the end of the talk here. But I'd like to start with a broader introduction and then continue with some additional details and some examples that I've drawn from some older work that I did with Gray Worcester. So I would imagine with this audience that everyone kind of knows what a mushy zone is. It's a porous layer mixture of solid and liquid that forms between a solid and its melt during solidification. You probably also know, most of you I guess, about the mechanisms, but the mechanisms are kind of important for what I'm going to say, so I'm going to explain it anyway. So there are two basic ways that this can happen. One, the melt could actually be solidifying, the solid could be solidifying into a melt that's colder than the equilibrium melting temperature. In that case, it's fairly obvious that an outwardly curved portion of the interface gains an advantage and is subject to a morphological instability where it runs away, initially forming fingers and then side branches, etc. That's not quite what I want to talk about here. Instead, I want to talk about mixtures that contain at least two components. And in that case, the mechanism is just a little bit more subtle. If we imagine here that this is solid growing up into a melt, it could be growing from a cold boundary in this case, so that the temperature gradient actually is stabilizing, so that an outwardly perturbed portion of the interface would actually tend to be melted back. But mixtures tend to reject their dilute components when they solidify. And so there's a buildup of solute in front of the growing front. And the melting temperature, of course, depends on this concentration of these species. This is why we put salt on roads in the winter, right? Although it also adds flavor, I suppose. But, yeah. So the melting temperature gets depressed inside this boundary layer. And so now an outward perturbation is in an environment that is both higher temperature and higher melting temperature, and those two things compete. And very often the latter effect wins, and you get a mushy zone. So here's a picture of a mushy zone. This particular one was formed by taking initially a very high concentration ammonium chloride solution that was at uniform composition and a temperature that made it liquid, and sitting it on a very cold boundary that you can just barely see at the bottom of this photograph here. I think the scale here is maybe 10 to 12 centimeters in the horizontal direction. And this material at the bottom is completely solid. This happens to be eutectic solid, but that's a detail that really won't be important in this talk. And then above it is a mushy zone. There's about 3 to 4 inches, I would say, of dendritic material there. It's almost pure ammonium chloride in this case. And the individual dendrites are a little hard to see. You can probably see that there's a kind of a vertical grain structure there. The stalks themselves are, I think, less than a millimeter wide, probably. And for the most part, they run the whole length of the mushy layer. There's a stark, so despite appearances, the solid fraction is actually pretty low. I would guess it's maybe like 15% there. And there's a strong density stratification. And in this case, it's an unstable density stratification. And so there is indeed convection. And perhaps the most interesting feature of this picture are these channels that form. They're called chimneys in some contexts. Sea ice people like to call them brine channels. And they're caused by the upflow of the material at the centers of convection cells. And somewhat ironically, the reason they form is the same reason the dendrites form to begin with. It's the melting temperature dependence or the dependence of the melting temperature on concentration. So the dilute material down here at the bottom sort of redissolves some of the dendrites. The enhanced permeability then causes a focusing of the flow, and there's actually a pretty vigorous plume that comes out of those things. So the key to understanding all this is the equilibrium phase diagram. I have two examples here. The one on the left is probably pretty typical of a lot of materials and also somewhat complicated. The one on the right is a more idealized and simplified phase diagram. It actually isn't a bad approximation for aqueous solutions like ammonium chloride. So if we had a material, say a sample of material at some temperature on the vertical axis and some average concentration on the horizontal axis, and if that placed it up in that region marked liquid, then once it reaches equilibrium, it will indeed be liquid. But we're mainly going to be interested when it falls in that little region labeled mush there, between a curve called the liquidus and the solidus. And when it reaches equilibrium in that situation, it'll be a mixture of solid and liquid. And the solid will have a concentration given by the solidus curve at that same temperature. And the liquid portion, or the interstitial fluid, as I'll refer to it in the mushy zone, will have the corresponding liquidus composition. So this talk is really almost all about the effect that the liquidus constraint has on the dynamics. Other than that, it might be a pretty ho-hum simulation of porous media and Stokes flow, which none of you are interested in, right? Yeah. Okay, so there are kind of two broad approaches to modeling these things. There are single domain formulations, which I really don't know very much about. And then there's a free boundary formulation, where you decompose the domain into a mushy zone, a liquid region, and perhaps a solid region as well. And I think the person that perhaps has one of the longer histories and certainly stuck with it longer than other people is Gray Worcester. And there's a very nice annual review article he has. If you're interested and new to this area, I recommend it. So all of these models have a couple of really key assumptions that they're built on. And it's really those next two bullet points there. The local equilibrium idea that I just talked about. Within the mushy zone, we're assuming there's this intimate contact between solid and liquid, and so the material is constrained to the liquidus. That means that the temperature and the concentration aren't independent, a point that I'll make several times probably during the talk. They're slave to one another. And then the other modeling assumption is, very familiar to people in this audience, that the mushy zone will be modeled as a porous medium with a solid fraction dependent permeability. And that solid fraction evolves as part of the flow. Okay, that idealized phase diagram I talked about makes an assumption of complete solute rejection. That means that the dendrites, I guess, in this entire talk, will be composed of a pure material. Again, that's true of some materials, like the ammonium chloride system. Sea ice tends to do that. But it's not always true. It's an incredible simplification. It makes things much, much easier. And I'll mention that a little bit more at the very end of the talk. We'll also assume a linear liquidus relationship. That's really not important at all. You could easily put in any shape you want, and it wouldn't change things too much. Just for convenience, I'll go ahead and assume equal density in both of the phases. There will be density stratification, though, due to concentration. We'll make a Boussinesq approximation where we only account for that difference in the pressure terms. And again, just for convenience, I'll assume that the thermal properties are the same in both phases, so that the thermal diffusivity, for example, will be the same in both phases.
I don't understand equal density.
Equal density, so the solid and liquid of the same.
So you're not going to have any convection, any movement of the due to density variations at all?
Nothing due what's called sometimes phase change convection. Right. So for example, the expansion of ice when it freezes, that effect won't be in here. But the density difference between ice and salt, that will be in here.
So they're not equal density. You're assuming that the density variations are purely due to
concentration,
to composition rather than due to temperature.
Due to phase, yeah.
So
Yep.
that's what that assumption.
Exactly. Yep. And again, that wouldn't be a very hard thing to relax. It just it adds a non-zero divergence to the divergence, the conservation of mass equation. Okay, so the equations. So the domains, in the first part of the talk, I'm just going to talk about a liquid region and a mushy region. And I'm going to kind of even ignore pretty much the boundary conditions at the very top and the bottom of the system, just to save a little bit of time. So in the liquid, we have Stokes flow with the promised buoyancy term. I'm going to ignore diffusion in this first part of the talk. That was kind of the point of the work that Nick and I did. We wanted to start relaxing some of these assumptions and see what happens. So in the second part of the talk, we will talk about a system with solidal diffusion in it. So you have just passive advection of the salt, if you like, in the liquid phase. This is an advection diffusion equation. The L's here indicate a Lagrangian derivative moving with the liquid velocity. Down here I've got some that move with the solid velocity. I'm assuming that the dendrites form a rigid matrix, and so there's just one solid velocity everywhere for the whole system. These ones that don't have a superscript, these are Lagrangian derivatives that move with the total mass flux vector of the mushy zone. I'll explain that a little better on the next slide. So moving down to the mushy layer, we have Darcy's equation with, again, that solid fraction dependent permeability and the same buoyancy term. And this is a way of writing the Darcy flux. Okay, so there's a lot of velocities rolling around. I think from watching other talks, I think people are familiar to this, but in principle, there's a fluid velocity, there's a solid velocity, there's an interface velocity, which can be distinct from these things. For the most part, I prefer to formulate things in the mushy zone in terms of volume flux. So it's liquid fraction times liquid velocity, solid fraction times solid velocity. It's, under my assumptions, it's divergence free, and it reduces to U in the liquid. And if you like, there's your Darcy flux. Okay, so a lot of this talk is about boundary conditions. There's kind of a lot of them. That's one of the disadvantages of the free boundary formulation. And if you're someone that advocates a single domain approach, you might really be shaking your head and wondering why. And I suppose one of the main points I want to make about this is the possibility of discontinuities forming in the system. And two things I might wonder about with a single domain formulation is, one, do you resolve those discontinuities? You probably do in some average sense, I would guess, if you're careful. But the other thing is that a lot of the information in the system is transmitted only one way. There's certain parts of the system that behave in a hyperbolic way, and characteristics play an important role. And I wonder if how that's accounted for sometimes. There must be some upwinding or something that has to be done to account for that. Okay, so some of the boundary conditions are kind of obvious from an intuitive standpoint. We're going to assume continuity of pressure, continuity of temperature, and for sure continuity of the normal component of the mass flux. The Stokes equations, or even if you want to do full Navier-Stokes, you're going to need an additional boundary condition on the liquid side of the interface. I guess people that are familiar with porous media might prefer a Beavers-Joseph condition, which allows some slip between the liquid and the solid. Other times you do see people just put no slip with respect to the solid phase. In these mushy zones, certain boundaries have a zero solid fraction on them. Not all the boundaries. But in the cases where we do have phi equals 0, we've typically argued for continuity of both components of the velocity at that boundary. And we actually use this boundary condition to derive another important boundary condition in one particular case. Okay, so the heat equation is second order, so we need another jump condition. This is the Stefan condition, which I'm sure most of you are familiar with. You can derive this with one of those neat little pillbox arguments. It says that the jump in the heat flux across the interface is produced by latent heat being released. So this is the velocity of the interface with respect to the solid phase. If this is 0, then there would be no jump. If you wanted different diffusivities, then move that in there, and you would take into account that as well. Okay, so the complications occur because of this. So within the mushy zone, the concentration, like I say, doesn't evolve independent of the temperature. So if you can imagine that you can solve the temperature equation first, you could then use the liquidus relationship to get the concentration. Oops. Well, and that means that if you go back to your solute evolution equation, the only unknown in that equation would be the solid fraction. Effectively, the solute diffusion equation becomes an evolution equation for the solid fraction. And the way that the solid fraction appears in that equation is only in first order terms. It's a quasi-linear PDE. And so characteristics are important. And it turns out that the correct boundary condition for initializing new characteristics is that the solid fraction, when you start a new characteristic in the mush, starts out at 0. And when there's no solutal diffusion in the system, the characteristics always move with the velocity of the solid phase. And so you can define freezing in this way. The mush is expanding relative to the solid phase. Okay, again, because of the neglecting of solutal diffusion in the liquid, there's a somewhat similar issue that you're only advecting the solute around. And in that case, the characteristics are trivial. They're just the trajectories of the parcels. And you can only specify the concentration on sort of the inlets where you start the characteristics. So outflowing regions from the mushy zone. But if a streamline comes and crashes into the mushy zone, the concentration is going to be fixed by the liquidus constraint, and there could potentially be a jump. All right, you need one more boundary condition. You need a boundary condition that tells you where the interface is, the free boundary condition. So this is on the mush-liquid interface. And for the most part, you can think of that as this condition here, which is actually a Stefan condition for the solute conservation across the mush-liquid interface. It doesn't look like a regular Stefan condition because we've killed the diffusion. And so the jump in the gradient that would normally be here falls down onto the jump in concentration. It's a jump in advective flux rather than diffusive flux. Later in this last part of the talk, you'll get a more normal-looking Stefan condition there. So when the interface is dissolving, that's the opposite of freezing in my definition, and when the flow is into the mush, you get this full equation, and that'll be the last thing you need to resolve everything. This condition simplifies in two cases. When the interface is freezing, but you have inflow into the mush, we've already said that on freezing interfaces, the solid fraction is 0 because of considerations about characteristics. And so the right-hand side of this equation vanishes, and you just get continuity of the concentration, but for a different reason than you might have it otherwise. If you want, you can recharacterize that boundary condition in different ways. So if you're familiar with this, you maybe are more used to that. Another special case is if you have a dissolving interface, but you've got flow out of the mush. In that case, the concentration is continuous due to the way information goes along solute characteristics. And so the left-hand side of this equation vanishes, and the free boundary condition, if you like, becomes solid fraction equals 0. And it's very tempting intuitively to think that that should just be the boundary condition always. And in the very early days when I was working on this, people often did that, but they only encountered situations where you had flow into the mush along freezing interfaces. Until you have strong convection, you don't encounter these other scenarios. And it turns out that in this model with no solute diffusion, this equation breaks down in that last scenario. When you have a freezing interface and outflow, it's freezing, so phi is 0 on the right, and it's outflow, so the jump in concentration is 0 on the left. So you have 0 is 0. Not a very useful free boundary condition. And the code won't work. You need another one. And the other condition turns out to be this, that the Lagrangian derivative of the temperature using the total volume flux as the vector field has to vanish on that type of interface. And briefly, the argument looks like this. So one of the reasons we were really interested in this is that that happens to be the type of boundary condition that you need on the chimney wall. And initially, we were trying to simulate chimneys. So since the concentration is fixed for parcels moving in the liquid, if you have say you're following a material particle coming out of the liquid, that means that the temperature has to go up on that parcel. If it didn't, it would drop back down below the liquid, and that would contradict your assumption there. Similarly, since phi is 0 along freezing interfaces, if you follow a parcel moving with the solid velocity, moving away from the interface into the mush, the solid fraction has to increase. If it didn't, it would become negative, and that would contradict that assumption. So you can take this inequality, those continuity considerations I mentioned earlier on interfaces with phi equals 0, and the solute diffusion equation, it's not solute diffusion, it's solute advection equation in the mushy zone, and you can derive exactly the reverse of this inequality. In other words, you get this boundary condition that I promised. Okay, so I wanted to give a few examples. So these are in what's called so they're 2D steady state computations. So this is a cartoon, but I'm going to have a few calculations here. So you can get a steady state if you force the material at constant velocity through a temperature gradient that's fixed in the laboratory frame of reference. Now this probably isn't something that happens in nature anywhere, I don't think. But it happens in laboratories, and it happens in manufacturing, and it happens in papers. Okay, so the dark curves here are streamlines for the Q field, the total volume flux, and the reason they're coming out the bottom there at a uniform rate is because of this uniform poling of the system. So the mushy zone is the gray material, and if you increase the Rayleigh number, there's only one Rayleigh number, it corresponds to solute. You can put in one for thermal effects as well, but in this model, I've only put in one. So if you increase the Rayleigh number, or really, to be more precise, these solutions actually tend to live on a subcritical bifurcation. So it's probably better to say as you increase the volume flux along that subcritical branch, as you just start to get an overturning flow, a pair of vortices, just after that point, it turns out that you dissolve your first hole in the mushy zone. And I refer to these as liquid inclusions, and I'm very fond of them because they exhibit exactly all four types of boundary conditions that I mentioned. Okay, so let's see. Maybe in the interest of time, I'll skip one slide here. Okay, so here's some examples from the computation. So it's 2D, it's steady state. The mushies, here's the mush liquid interface in dark. Below it is mush, above it is liquid. The streamlines are as I described before. Notice they go out the bottom. And those dashed curves are solid fraction contours. And so I've been following the subcritical bifurcation just to the point where you get a tiny little bit of recirculation, but everything is still solid. Give it just a little more oomph, and that recirculating region gets a little bit bigger, and you get your first hole in the mush. And you can actually use those boundary conditions I just showed you to prove that that has to happen at the lower stagnation point. And in fact, one time that saved me from making a mistake in a code. It wasn't those kind of easy mistakes you guys have been talking about. The code didn't crash. It was a sneaky mistake. It was a factor of 2, and that stagnation point wasn't on the bottom of that thing, and I couldn't figure out why. And eventually, it found the factor of 2. But. Okay, so initially we were doing this to get chimneys. I won't claim that this is state of the art. I know that there's at least a couple people here that I think have worked on this out. Probably better calculations out there. But this was at the time a success for us. So these are solid fraction contours, and there's now very strong convection. So there's still a flow at the bottom, but it's pretty negligible compared to the recirculation. And so you get a pretty violent plume that completely blows the top off. And these are now on the upper branch of
Mr. Mike,
Yeah.
2D or 3D calculus?
Still 2D. Yeah.
Is it axis symmetric or?
No, it's really 2D. And that experiment I showed at the beginning, that was done in like a Healy-Shaw cell. So.
And then in that experiment, those features were also one line, or were they?
Yeah. So I said Healy-Shaw cell. That's maybe a little exaggeration. I think it was 1 centimeter wide. And so sometimes the chimneys like the wall. So they would tend to grow on the walls. But it was essentially a 2D flow. If you repeated it, and I'm sure people have, with a real Healy-Shaw cell, then they would go the whole. It would be very two-dimensional. But for sure people do this in 3 dimensions. It's just at the time I was doing 2D calculation.
Or axis symmetric?
Or axisymmetric, yeah, and that's for sure been done. Okay, so one other thing that I thought I'd talk about briefly, because this audience, in a ternary system, things get more interesting. You get 2 different types of mushy zones. So let's see if I can get this right. So this top one is largely comprised of just one dominant species. We call that the primary mushy layer. And the constraint there is on a cotectic surface, or liquidous surface. And down here, the mushy zone is comprised of 2 of the 3 components. And the constraint is to a cotectic curve on the phase diagram. And this is actually the one that was misbehaving, and I realized the stagnation point was in the wrong location. Another interesting thing about this system is that you get 2 different Rayleigh numbers, one for the primary mush and one for the secondary mush. And so you can dial those back and forth. In this case, we've got the convection primarily in the top layer, but you can make it happen in the bottom layer, or you can make it go in both layers. Okay, so now I want to move to the topic of the title of the talk. I'm going to change a few things. It's not a coincidence. I kind of gotten out of the mushy layer business for a while, but I had this student that was really keen to get back into it, and I'm glad he did. And I wanted to think about things I hadn't really thought about before. So for one thing, it seemed like this no solute diffusion thing was causing a lot of trouble, so I wanted to put the solute diffusivity back in. Now I should mention that causes some trouble of its own. That boundary layer I mentioned ahead of the mush interface, it's also unstably stratified. And when it goes unstable, you get a much finer scale convection. And it's very hard to resolve those things numerically. And that's one of the reasons why we didn't want solute diffusion. But in this part of the talk, I'm not going to have any density stratification. There's going to be no flow whatsoever, so that won't be a problem. Also, I wanted to look at time-dependent solutions. In particular, I wanted to move away from that crystal pulling geometry and go to a more natural geometry where the growth is from a fixed pole boundary. I'm going to go ahead and ignore latent heat in this part of the talk. This is mainly just because it makes it very clear what's happening. It's not so much that you have to do that. And the equations, when I show you them here in a second, they're going to be non-dimensionalized. Okay, so here's the scenario we have in mind. So I've drawn it in 2 dimensions, but really I'm only going to do one spatial dimension, the vertical one, and time. Okay, so these are results from very early in the simulation. So it's kind of like that experiment. You mix up a bucket of stuff, and you set it on a cold boundary, and you let it go. And as I say, this is early in the numerical experiment. The solid part of the growth is very, very thin at this point. But the mushy layer is somewhat, developed. And here's the solid fraction as you go through the mush, and then it drops to 0, of course. And the plots here are the temperature field. It's cold on the bottom, warm on top. You can see the evidence of the liquidus constraint here. Those 2 curves are related to each other by a linear relationship. And it may not look like there's diffusion in there at this point, but there is. And on the next slide, I'm largely working with the liquid fraction instead of the solid fraction. Okay, so the equation. So the solute field, we set the flux to 0 up at the top of the tank, so we want to conserve solute, so we don't want it diffusing out of the tank, so to speak. At the bottom, that's not an issue because we're going to ignore diffusion in the solid phase. The hot temperature becomes 1 at the top, 0 at the bottom. Notice that the heat equation is exactly the same. It's the same in the liquid, same in the mush, same in the solid. That's for my simplifying assumptions. Equal thermal diffusivities, and I'm ignoring the latent heat. And the reason I like that is now we can just solve for the temperature. There's only 2 variables here, temperature and concentration. If I know the temperature, and then if I move to the mush here, and I prescribe this liquidus relationship, I then know the concentration. So the only equation that's left is the solute diffusion equation. In the mushy layer, the concentration picks up a factor of liquid fraction on each of the 2 terms. Again, I know the concentration, so this is now an evolution equation for the liquid fraction. And it's a first order PEV. Now the boundary conditions, now we have no jump in temperature, no jump in the heat flux, no jump in the concentration. We now get a proper step-on condition at the mush-liquid interface. If you like, you can think of that as the free boundary condition in all scenarios in this case. Okay, so one of the first things I asked Nick to do was to find a steady state. He came back the next day and said there's no mushy layer. Well, it's kind of obvious if you think about it for a while, but I wasn't used to that. So just think about what happens in the case where you let the domain be semi-infinite. So that's kind of a textbook example. People use the similarity solution to analyze that case. In that case, the mush-liquid interface grows forever. It advances like t to the half. And that's because there's an infinite reservoir of salt in the semi-infinite domain. And so it never runs out of material to grow with. Another contrasting situation is even if you put it in a finite domain, so that you will run out of salt, but you shut the solidal diffusion off, like we did in the first half at the top, you get a steady state with a mushy zone. But when you turn the diffusion on, if you're very patient, the dendrites, they gradually diffuse away. Okay, so let's figure out how that happens. So this is the only equation left that we have to solve. If we expand that a little bit, we see that it is indeed a quasi-linear PEV for the liquid fraction. So the characteristics, if you like, they move with this velocity, minus epsilon Cz over C, where C is already known because we solved numerically or otherwise for the temperature field. So it's a non-trivial function of C and T. Very different than what happened in the first part of the talk, where the characteristics were always just a constant velocity, all parallel and whatnot. Okay, so again, along curves Z of T satisfying this equation, the liquid fraction evolves according to this equation. Whenever you have to initiate a new characteristic, in other words, when the interface velocity is faster than the characteristic velocity at the interface, you initiate then with 0 solid fraction, or 1 liquid. So there's 2 scenarios. The characteristics can move slower than the interface, in which case you only initiate them, or they can move eventually faster than the interface, in which case they crash into the interface. Along this type of boundary, or portion of the interface, you don't need to do anything to the liquid fraction. You only need initial conditions back here. And in either case, the location of the free boundary, as I said before, can be determined by the step-on condition. All right, here's some examples. Looks like I'm going to run ahead of schedule. So 2 examples. On the left, this is from the similarity solution. So this time there's no top. It goes all the way to infinity. So this is the mush liquid interface. Z is a function of T. It's a parabola. Turned on its side. And same thing down here with the solid mush interface. And in between, these are the characteristics I'm showing you. And they never run into the mush liquid interface. The solid mush interface actually is a characteristic, it turns out. If we put the top back on, then we get this type of picture. So eventually, so at the beginning of the experiment, it looks like the mush is growing like crazy. But eventually, you run out of salt in the far field. Things slow down. The characteristics catch that. And in fact, it starts to roll it back. And eventually, it dissolves the whole thing away. So the mush liquid interface, sorry, this is mush liquid, and the solid mush interface, they meet each other. And in fact, the solution, of course, continues, but you only have a solid liquid interface there. Yeah?
Does the size of the domain tell you something about that characteristic time when it does the turnover?
You want the turnover, or you want, yeah. So I was hoping you were going to ask about that. But, size of the domain.
Presumably,
there's obviously a diffusion length scale that you could get that would give you that. Yeah.
so presumably at early times it does look like the left-hand picture.
For sure, yeah, and we've done that, and yeah, that's right. Or you could think of it this way: if you made the top really, really big, right, and you didn't have much patience, then you would still get that picture, right? Okay, so after they crash together here, it continues as a solid liquid interface. It doesn't grow as fast. And that's exactly the interface, the front that you would get if the morphological stability hadn't been there. The condition for this to end is that the temperature field is no longer rising slower than the melting temperature field, if you like. So the conditions that cause morphological instability have ceased to hold at that point. And in fact, I wish I should have put one more figure in, but I got tired of downloading them. If you drew that solid liquid curve, it actually extends back into this region as an unstable solution. Okay, so just to kind of wrap up, Nick and I have done a couple of other things involving the eutectic situation, where you cool below the eutectic concentration. And basically, you know, all these constraints that you put in there because of the phase diagram, they do kind of interesting things to the PE, and you have to think about it. The thing that we're trying to work on now is relaxing the vertical solidus assumption. And so far what we've discovered is it's not really a big deal. It's pretty easy when the solid fraction is increasing, in the sense that if you watch a point fixed to a dendrite, if phi t is greater than 0, you just have to make a small change to your code or whatever, your formula. If, on the other hand, that's negative, then you've got a whole new can of worms, because you have to know the history of the material that got solidified. Now, there it depends a little bit on time scale. If you're going to neglect diffusion in the solid phase, then that history is permanent, and you would just kind of unwrap it as you melted those dendrites away. But if you were on these geological time scales or whatever, then you might want to account for some diffusion in the solid phase as well. Okay, that's all I have to say. Thank you.
Good. We have a couple of minutes for questions. You're on. So in that calculation you were showing, there was no latent heat. Is that correct? That there wasn't a feedback.
In the last one, and again, I did that just so that it was very clear that you could already solve the temperature field, and you can see very clearly that the liquid is constrained. Turn that other equation into a first-order PDE. Numerically, you could put the latent heat back in without too much trouble. You would just iterate on that. So in the past, you know, I've done parameter studies on the other system, looking at the effect of latent heat. Oftentimes, it's only kind of a small change. Oftentimes there's not a big qualitative effect due to the latent heat. I know at least one counterexample of that. But you can think of it as making the kind of the first order phase transition to second order. There's no latent heat there.
Better questions?
So, just following up on the previous question, does latent heat it must become more significant if you only have a single constituent material that's freezing or thawing? Because that's the only thing that would drive the process.
Well, yeah, I know people always find this counterintuitive when you tell them you're ignoring latent
If
heat.
you have a pure water,
Yeah.
the classic example with pure water is you have an enthalpy, which is sort of a curve coming straight up here. It's a slope, a specific heat coming up. You have a flat zone where the
Yeah, I understand what you're saying, but I mean, there are phase transitions that don't have latent heats, and they still have fronts that propagate. So you don't really need it. I'm not saying it's not important. Like, you might want to have it there for quantitative reasons, but it's actually a very common assumption in the solidification literature to simplify. Some people, yeah, I mean, there's countless papers that do that type of thing.
Are there any conditions under which the diffusion can drive flow?
Fusion can drive flow.
Well, I guess under which a problem like this can have flow. I don't know if diffusion could drive flow. Maybe that's too vague.
Yeah, I mean, so you could have buoyancy, you could have the change in phase upon solidification. That can drive a flow.
Would buoyancy actually drive a flow in this case?
Sure, yeah.
Yeah.
I mean, so there was a concentration gradient. If it was, the right way around, right, then it would be an unstable stratification. That's what was happening in the first part of the talk. It's, Rayleigh-Benard convection.
Okay, so you could actually have the same kind of flow as you had.
You could, yeah. I took it out just because, I wanted to focus on just this issue and highlight this issue with the characteristics.
All right. In that case, let's thank Tim again.